Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to module 2.4, and as you may recall, what we have been doing in this week is we have been trying to obtain what we call these NEGF equations, and it involves kind of two steps. The first step being take the standard Schrodinger equation, which is E psi equals H psi, and to account for the contacts, or rather as a result of the contacts, you get these two additional terms. The first term tells you about outflow from the channel, and the second tells you about inflow into the channel from the contacts. So those are the two terms that come in. And each one of these, in principle, has a component due to contact 1 and a part due to contact 2, which is why the way we wrote it is this sigma has a sigma 1 plus sigma 2. And the sigma is non-Hermitian, and if you look at its anti-Hermitian part, sort of, sigma minus sigma dagger, the part that would be, this is what would be 0 if sigma were Hermitian, because Hermitian means a matrix being equal to its conjugate transpose. So that's what's called gamma, and that's like the escape rate. That's what physically tells you how easily electrons can escape from the device. And then there is this term which tells you the strength of the source term. And that is what we argued is kind of related to the escape rate. If you had a contact well coupled so that electrons can escape easily, similarly the source term describing how electrons come in from the contact will also get bigger. That's sigma n. And here again you'll have two terms, gamma 1 F1, gamma 2 F2. Here also I've just written gamma equals I times sigma minus sigma dagger, but the thing is it applies to the component due to 1, like gamma 1 is I sigma 1 minus sigma 1 dagger. Gamma 2 is I sigma 2 minus sigma 2 dagger. And when you look at the total thing, then gamma is I sigma minus sigma dagger. Same way. Okay. Now the basic NEGF equations, the two equations that we have obtained so far then, one is this one for the retarded Green's function and the second one for this non-equilibrium Green function. And as explained, that non-equilibrium Green function, Gn, that is like the matrix version of the number of electrons. And if you take the trace of that matrix, you get the total number of electrons in the device. So when people solve the equations for a particular device, of course the first step is to obtain H and sigma, and how you write H, that's what we described last week, and how you write the sigmas, that we'll talk about as we get into do some real problems after this. But once you have those matrices, it's straightforward matrix algebra, because once you have H and sigma, you can calculate this retarded Green's function, and then you can calculate this non-equilibrium Green function, the Gn. Calculate that. Now once you have that, then you can actually calculate quantities of interest, quantities that actually can be compared to experiments. And one of those quantities is the density of states, because as you know, a very important advancement in nanophysics is this development of scanning probe microscopy, scanning tunneling probes, where you have a small probe that comes down on the surface, and by measuring the current, you can measure the local density of states around that point. And as you move it along, you can get a map of the entire density of states. And in fact, that's how people take pictures of the surface with atomic resolution, is that they look at how the density of states varies across the surface. So one thing we'd like to be able to do with models of this type is to calculate the density of states. And that's what this third equation is about. So let me say a few words then where that equation comes from. This A, that's like the matrix version of the density of states. You see, just as Gn is the matrix version of the number of electrons, the A is the matrix version of the density of states at a given energy. And this one, I'll try to explain where that expression comes from. And the other equation that you'd need is the expression for the current. So now, let me explain where that one comes from. So what we had is, you see, Gn is equal to Gr sigma n Ga. Now the sigma n we discussed is this in-scattering, the rate at which electrons come in from the contacts, and this has two parts, the part that comes from contact 1 and a part that comes from contact 2. Now, and this will then tell us the electron density at a given energy in the channel. Okay. Now the point I wanted to make is that if you want the density of states, then you see one way to find it is by saying that supposing at this energy the states in the contacts are all completely full, which means that the corresponding Fermi functions happen to be 1. Both contacts. Now if the contacts have Fermi functions of 1, then you see we expect that the states inside the channel will also be completely full. They will just be in equilibrium with both contacts. Because you have one contact trying to fill it, another contact trying to fill it, trying to get a occupation factor of 1, well, so it will basically be filled. And if all the states are filled, then of course the electron density that you get, number of electrons you get, is basically the number of states. Because remember, we have the states which are filled with electrons. So what Gn tells you is which of these states are filled. And the argument I'm making is, if at that energy the contacts have Fermi functions which are equal to 1, then all states are filled, and so what you calculate for Gn should essentially be the density of states. So that's the quantity we'll call A. That's this, actually the technical name is spectral function. And that should be equal to Gr times sigma n under the condition that F1 and F2 are both equal to 1. And so you get Gr times gamma 1 plus gamma 2 times Ga. That's it. You see? So what you have done is, you can write the expression for A as this gamma 1 plus gamma 2 is what we have been writing as gamma. That's the total thing when you have added the 2. So you could write A is equal to Gr gamma Ga. So that's the basic argument. And if you look at the equation I had here in number 3, see, that's like the first part of the thing. Gr gamma Ga. Now you'll see I have two other expressions here, and that needs a little bit of algebra. In other words, to get this one, I used a physical argument, namely that density of states is just the Gn when all the Fermi functions are 1. That's a physical argument. That's what got us here. But to show that this is equal to this, is equal to that, that's pure algebra starting from here. And so I won't go over it in this lecture. That's in one of the tutorial lectures. So that's one of the homework problems where I say that, well, given this equation for Gr, show that that quantity is equal to this and is equal to that. Okay? So let me now move on to the current equation. Because the other important quantity that you can measure experimentally, usually what you're most interested in, is the actual current in the device. See? And this is where, if you remember, what we had done earlier when we were doing the semi-classical treatment, and then we did the one-level thing, which was possibly module 2 of this week. We started from the time-dependent Schrodinger equation, because you see, this is the time-independent one. Now, whenever you want currents, you kind of have to look at the time-dependent thing, the IH bar, where instead of E, you actually have a IH bar ddt. Because if you start from here, then what you can do is obtain an expression for the ddt of psi dagger, which is like the current then, because the rate at which the number of electrons changes, that would be that is what you should identify with current. So if you have, so what we want to do is calculate this quantity, IH bar d dt of psi dagger. And once again, if you use the chain rule, you'd get something like this. And by the way, I'm doing this without including the source term for the moment. So for the source term, we'll talk separately about. Let's just do the without it first. This is IH bar d dt of psi dap times psi dagger plus psi times IH bar d dt of psi dagger. So that's just the chain rule. So for IH bar d dt of psi, we put in what we have there, which is H plus sigma psi. And for this one, of course, I need the conjugate transpose of that, which, if you take conjugate transpose here, when I, because of the conjugate, you'll pick up a minus I, so you'll get something looking like this. And this is where you have to be careful, because when you take H psi and take conjugate transpose, it also reverses. So it's like psi dagger, H dagger. And H, of course, is Hermitian, so H dagger is the same as H. So put it that. And then psi dagger, sigma dagger. Okay. So this is what you can replace in here. So what you'd get then is, instead of this, you'd have minus psi dagger H minus psi dagger sigma dagger. So what we have then is this expression for d dt of psi dagger. So I can take this off from here. We'll write it up here. That's equal to H psi dagger plus sigma psi dagger minus psi dagger H minus sigma psi dagger sigma dagger. Sorry, I guess there should be a psi in psi dagger H, and there should be psi dagger sigma dagger. Sorry. Okay, that's it. So what we have written down here is IH bar d dt of psi dagger. And remember, this psi dagger is what we had defined earlier as something like this. If you look here, that's this G, what we call Gn, the matrix version of the number of electrons at that energy. Okay. Now, what you have here, you might look at this, and you'd say, well, they kind of look similar, but don't really cancel. Because remember, when you have matrices, you cannot change their orders. When you're dealing with numbers, A times B is B times A. But with matrices, H psi dagger is not the same as psi dagger H in general. Okay? But what we'll be doing is, since we are interested in the change in the total number of electrons, we could take the trace of this. You see? Because total number of electrons, as we had argued, is like the trace of Gn. So let's take the trace of both sides. And one of the important properties of trace is that trace of A times B is equal to trace of B times A. In fact, if it is three things like A, B, and C, then you can rotate it cyclically. So you can bring the C back here and it would look like CAB, etc. So trace has that property. So if I am going to take the trace of both sides, what we'll have then is IH bar d dt of something like what we could think of as number of electrons n by taking the trace. And on this side then, those first two terms will cancel completely. Because H psi dagger, and this is like psi dagger H. So that just cancelled. Trace of this is the same as the trace of that. Here, what we'd have is the trace of sigma minus sigma dagger times psi dagger. That's it. So you'll have one term which is sigma psi dagger and another term which would be sigma dagger psi dagger. Here it looks like psi dagger sigma dagger, but once I take the trace, I could take this from here and put it out in front because I can always turn them around cyclically. So that's what this one is. And so I can write dn dt then is equal to minus trace of sigma minus sigma dagger over I h bar without the minus. And then the psi dagger is again like n. So dn dt is equal to this quantity times n. And this quantity, this I from here, I could make it minus I up here. So I could put an I here and a minus sign. And this is what we have called gamma. See? And so you have to take the trace of gamma times this psi dagger. So the psi dagger is like gn over 2 pi. That's the matrix. So the point is, you'd have to take the trace of gamma gn. So this would be like minus trace of gamma gn over 2 pi. Okay? And the h bar, sorry. So this is the quantity then, would be like dn dt is equal to this, and that is what would be like current. Okay? So let me write this up here, and we'll just talk about the physics for a minute. And the algebra is done. So it's like when you take dn dt, what you have is minus 1 over 2 pi h bar is like 1 over h, and then trace of gamma gn. Okay. Now, the gamma has many terms in it. Like, if you have two contacts, it has a gamma 1 and a gamma 2. And the way you would interpret this then is, gamma has these two parts, the gamma 1 and gamma 2, which we associate with the two contacts, contact 1 and contact 2. So you could say that the current from contact 1, that's what is like determined by the gamma 1 gn. So you could, if you wanted contact 1 current, you take minus 1 over h trace of gamma 1 gn. And if you wanted contact 2, you'd put trace of gamma 2 gn. And when you add the two, it's like I1 plus I2. That's the total current from the two contacts, which should add up to the rate at which the number of electrons is changing inside. Now, usually when we write current, of course, we write charge current. This one, the way it is written, would actually just give you the current per second, per unit energy here. And so, instead, if you want the charge current, you should put a Q here. Okay? So if you look back then at the equation I was trying to get, this current expression, which is current at terminal P, P meaning 1, 2, whatever, we got Q over H trace minus gamma P Gn, you see? So that's the thing in red here. What you don't yet have is this first term, the black one, and that I'll explain in a minute where that comes from. But what we have is the second one. Now, just to explain that where the first term comes from, the idea is that you see, we started from this modified Schrodinger equation, which looks like E psi is equal to H psi plus sigma psi. What we didn't include in this discussion was the plus S, this part, the source term part of it. If we had included that, we'd have got this other term as well, but it takes a little more discussion. An easier way to get that other term is to again argue that our expressions must be such that at equilibrium they give us the correct answers. So you could say that, well, this tells you the rate at which the current at contact 1, where electrons are, flowing, this is only gives you the term that is flowing out. There's of course another term due to that source term which comes in, which must exactly balance it at equilibrium. So you could say the other term must be whatever this one is at equilibrium. So you could say that I need to add to this plus I1 at equilibrium. Now how would you find the equilibrium current? Well, that's where you could argue that, well, in general, we have seen that Gn is equal to Gr times gamma 1 F1 plus gamma 2 F2 times Ga. And at equilibrium, both contacts have the same Fermi function, F1 and F2. If they are the same, then as I have explained before, it's like if two contacts are both trying to impose the same F, then that's the equilibrium situation. The non-equilibrium is because there's two contacts trying to impose two different Fs. So if you put the same F in there, then this becomes Gr gamma 1 plus gamma 2 Ga, and then the common F, whatever it is, for that contact, you see. And this is the quantity that a little while back in this module I argued is actually the spectral function A, the matrix version of the density of states. So the point is then, this equilibrium term you could write as exactly the same thing, plus Q over H trace of, but this is where what you'd get is A times F times the gamma 1. So you'd have A, F, gamma 1, because Gn at equilibrium is that quantity. It is the spectral function times F. Because if it's at equilibrium, then the density of states is filled up according to F, and that's what gives you the electron density. And then, so now you can see how you get that first term there. That would be one justification for it. It is just like that term, but whatever you'd have expected at equilibrium. So that sort of gives you then all the equations you actually need to analyze the devices. And this is where I say that, all of this is, I'm presuming, is new to most of you, at least, possibly to all of you. And it takes some time to get used to all this. But one point I stress is that there are kind of different parts to this, different aspects of this, which you can do separately. Because one of the first things is, where do these equations come from? And so far this week, I've been trying to explain that, give you a feeling for where these equations come from. And it basically starts from Schrodinger equation, modifies it to include certain things in the contacts, and then obtains an equation for psi-psi dagger. Schrodinger equation is an equation for psi. These are equations for psi-psi dagger. That's kind of what we have done so far. So that's the first thing. Where do these equations come from? The next thing is, how do I use these equations to calculate something useful? And a third question is, when I've calculated something, how do I understand them? And those last two things can kind of go together. You should calculate and try to understand, etc. But the part about where the equations come from and how I use them are sort of two separate things. You could be an expert at one and not be very good at the other, for example. You see? So what we have done so far, the first 4 modules, we have talked about where these equations come from. In the last 2 modules, we'll try to talk about a little bit about how you apply them to different things. Actually, we'll take simple one-dimensional examples. And in the coming 2 weeks, that is week 3 and week 4, we'll be talking about more difficult problems as you go along. It would all be applications of these equations, you see. But in terms of where these equations come from, I won't be saying very much more. So basic equations are 1 and 2, and then if you want to obtain results that can be compared with experiments, that's when you need the 3 and or 4, depending on what you want to compute. But as far as where these equations come from, you can look at the notes, and we have more or less discussed as far as we want to go into it. And after this, let's talk about how to use it.